So I hope you had time to relax for a moment. I like to continue with section 2.2, which is actually even shorter section than 2.1. So 2.2 does two things. It gives us some properties of determinants, which will be helpful in chapter 2.3, when we actually show that the determinant really determines if the matrix has an inverse. And the other thing what section 2.2 does is it connects the calculation of the determinant to the Gauss algorithm. And it turns out that is actually the fastest way of calculating a determinant, and it's a Gauss algorithm again. So the reduced row echelon form or the row echelon form is again what we can use, this time not to solve a linear equation this time to find the determinant of a matrix. So these are two things, a little bit properties of the determinant, preparing for section 2.3, and giving us a better way in some way of calculating the determinant. Okay, I share my screen again. So we go to section 2.2, and the title is Evaluating Determinants by, this time not row expansion, this time by row reduction. Because Gauss algorithm works usually row by row to generate our leading ones. The first result in this section is we will not show, but it turns out it's kind of obvious with our definition. And so in your book, the first result is theorem 2.21, and I combine it with 2.22. And the result says the following: you have a square matrix n by n, a n by n matrix. Then we have two things. Number one, that's obvious from the way we calculate determinants. If one row or one column of A has only 0 entries, then the determinant is 0, because we just take this row or this column as the row for a column for our expansion. So the first property is very clear by the way how we actually calculate our determinant. So if one row or one column of A is entirely 0, then determinant of A is 0. That's kind of obvious, because if we have a row with really only zeros, then we just use this row for our expansion. And the next property, that's 2.2.2 in your book, is we can use row expansion with respect to rows or columns. So it turns out row or column for a determinant really doesn't make a difference. So that means if you calculate the determinant of A or the determinant of A transposed, you will get the same result, because row or column are totally interchangeable here. So determinant of A is equal to the determinant of A transposed. So it doesn't matter if you look for rows or columns. So both of these results are actually kind of obvious. The next result is in some way more, these are also important. The next result is more important for the calculations we do later on. And again, some of them are very easy, but some of them are harder to get. But you can always show them with what I showed you. The second definition of a determinant is with the help of the permutations. The permutations actually show these properties actually more easily than what we did with the row and column expansion as our definition. So this is in your book is theorem 2.23. These are now important ways of how we can calculate a determinant. And I will formulate this only for rows, because rows and columns are doesn't matter for a determinant. I could have written this as for columns. I'd only write it for rows, but if you ever need it for columns, it's the same. No? So I only write it for rows. So again, A is an n times n matrix. And again, I go row by row now. But it's really not important. The same will be true for column by column. So A1 is the first row, A2 is the second row, and then somewhere down the road is an AI, then somewhere here is an AJ, and down at the bottom, sorry, is an AN, the last column. No? So here is row I, here is row J. And I single them out because I like to do something with these two rows. So it starts with AN to A1 to AN. Somewhere arbitrary is a row AI, somewhere is a row AJ. And now the question is, if we change these two rows in 3 different ways, how will this change the determinant? Okay, so this is what this is about, this result. So result number 1, and that's actually very easy to see also with our definition. So if you do the following, you take, remember this is our matrix, these are the rows, and everything is the same. But then you take one row, and I just pick row I, it doesn't really matter. So then here comes row I, and down on the bottom is row N. I didn't even indicate row J. And now what you do is row I is multiplied by a constant alpha. So you have an alpha multiplied. So alpha is in R. So how does this affect the determinant? So what is the difference between this determinant and this determinant? And now you say, oh, I just take row I for my expansion. Then every number has an alpha. So I can just factor the alpha. And that is actually what's happening. So if you multiply one row by a number, the determinant is multiplied by this number because you can just factor it. So this is easy to see. Part B is a little bit more difficult to see with our definition, but easier to see with the permutations, but I will not go into this. A1, A2, dot, 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 up to AN. And now what's happening is here I have row AI, here I have row AJ. And now I flip the two. So the J goes to I and I goes to J. I flip the two rows. And now from the definition about with the help of the permutation is clear, because it would mean every permutation which is even becomes odd and every permutation which is odd becomes even. So it turns out the determinant just gets a minus sign. With our row and column expansion, that's actually much harder to see, but nevertheless, if you switch two rows in a matrix, the determinant gets a minus sign. And then finally, again, something which is harder to see. Also both of them would be easy to see with the help of the permutation. The other one is even harder to see with the permutations. So what I do now is I write down the matrix again, A1, A2, somewhere down the road comes AI, and all the rest. And now what I do is I take row J, multiply by an alpha, and add it to row I. So you take one row and add it with a multiple to another row. It turns out that doesn't change the determinant. That is equal to determinant of A. Again, alpha can be an arbitrary number in the reals. So adding one row to another row doesn't change the determinant. And as I said already, this is pretty easy to see. That really involves more work to understand why this doesn't change. It comes down to the fact that if you have a determinant with two equal rows, in our book, actually that's a later result, but actually you would prove this before you prove this. If you have a determinant with two equal rows, turns out then the determinant is always 0. So that's actually behind this result here. Even the book doesn't mention it at the moment, but if you ever in your life have the desire to prove something like this, so this is what you should actually prove first, that if you have a determinant with two equal rows or two equal columns, then the determinant is automatically 0. As I said, in our book, that shows later up, but actually you should prove this before you do this. Okay, so this is just something for us now to remember. And now our elementary matrices come back. The elementary matrices are the matrices which we use for matrix multiplication doing the Gauss algorithm.
I'm sorry, Professor. Did you say that if two of the rows are the same, the determinant is 0?
Yes.
Okay.
Or two of the columns. And like I said, in our book, that comes later as a result out of this. In reality, this is something you should actually, let's say, if we would really prove every result in our class, which I will not do because it also would take too much time, that is actually something which is easier to see than this one. And once you have it, then it's easy to show this guy here. Yeah, so it's just, if you're ever interested in how is this all proved, then what I just mentioned would go actually first. First, you have to understand why is it that a determinant with two equal rows of a matrix with two equal rows, why is it that it's actually 0? And again, when you think about the permutation, it's not so hard to understand because essentially there are always two numbers which each time are the same. So if you flip them, you make the permutation odd to even and even to odd, they always come up with a plus and minus. So every term essentially shows up with a plus and a minus, so they all cancel out. So that's kind of the idea behind this.
And since their determinant is 0, they're not inversable, right?
Right. That means a matrix with two, I mean, that's the next step, no? Also, once we know that the determinant is 0, then in the next section we figure out if the determinant is 0, it has no inverse. That means a matrix with two equal rows or columns has no inverse. That is the next step. Okay, so, but now, as I said, we come back to our elementary row operation matrices. And again, in this chapter, they will be helpful to find our main result in the next section, actually. So we had 3 of them. There was the multiplication matrix. So this has just ones. Then there's somewhere in alpha and somewhere in alpha. And this is in row I. No? So this, when you multiply this with a matrix, from the multiply row I by alpha. Then something I called the switching matrix, Sij. So here we have ones, then there's a 0, then we have ones, then there's a 0, there's ones, and then this one moved here, and this one moved here. And this is row I, and this is row J. So this is a matrix. When you multiply it from the left with the matrix, it switches row I and J. And then finally, from the notation, the most complicated one, I alpha J means add alpha times row J to row I. So this thing looks like this. It has ones along the diagonal. And now in row I, add column J is, also here is an alpha, no? So this matrix, if you multiply from the left a matrix with this, then it will add alpha times row J to row I. Now for these matrices, Because this is a diagonal matrix, we know the determinant is the product of the diagonal. So it's alpha. This matrix is a lower triangular matrix, or if the alpha up is here, then it's an upper triangular matrix. The determinant is the product of the diagonal. It's 1. This matrix is a switch from the identity matrix. Identity matrix has determinant 1. According to this here, the determinant of Sij is -1. So it turns out for each of these guys, it's very easy to find the determinant. So I write this now down in the next result. So this is actually, the next result is actually easy to show, so I don't even go any detail, not because it's too complicated, it's just really, it's always just one line to show it.